We'll start a new topic, uh, containerization, okay, and mostly about Docker, okay. So what is Docker, okay, or what is a container? So if you see on the screen, you can see there are some big containers, okay, and there is a ship in the form of dolphin, okay. This is the image for Docker. Okay. So if you see the ship or the dolphin like ship is carrying some containers. These are the containers which are shown on the left hand side. Okay. The same thing resembles Docker. Okay. So what does these containers contain? They contains wooden blocks. Some blocks are there. So if we move these blocks, okay, via ship from one place to another, the contents in the containers, okay, that is wooden blocks, will remain intact. They won't uh, mix up. Okay, so whatever we have at one place inside the container, if we put that container at some other place, okay, the contents inside the container will remain same. Okay, the same approach is used in Docker as well. Okay, so how we'll see next. Okay, so if you see this image, earlier before DevOps, we were saying that it works on machine, and after DevOps, we'll be saying that it works on my container as well. Okay, so how we'll see that next as well. Okay, so same kind of image. Before DevOps, it works on machine, but after DevOps, we'll be mostly saying it works on my container. So I'll give an example. Uh, Suppose I've installed a software, okay, which is a Java based software. Okay, so suppose a developer has installed the software rather than I will say the developer has installed created a software which is in Java. Okay, and it is working on his laptop. Okay, he worked on this laptop. It is working on his laptop, and after his testing and all is done, he gives it to the operations guy, okay, to deploy it on the server. Okay, so when the operations guy deploys it on the server, okay, he comes back to the developer and says it is not working. Okay, so the developer says that no, you must have missed something, or you don't know how to do that. It is working on my laptop, okay, but it's not. You need to check something, okay. The operations guy again checks for something, okay. Still he says no, your code is not correct. He asks developer to look into it. When the developer goes on the server where it was deployed, he sees that the Java version on which he has created that software was something called 1.7. Okay, and in the on the server it is 1.6. Okay, due to this compatibility or dependency, okay, and some packages were also missing which are required, okay, for software to run. Due to this dependency hell, okay, the software was not running on in the production on the servers. Okay, so whatever then what the developer did, he created a document, okay, that with the prerequisites that it should have JDK or Java version 1.7, and this operating system, and this dependencies should be installed before deploying the application into production on the server. Okay, and gave it to the operations guy. Okay, still the operations guy missed something. Okay, even after following the documentation, the operations guy missed something. Okay, because he is a human being, he will make some mistakes. Okay, again the same cycle repeated. They both started blaming each other, that is the development team and the operation teams. They started blaming each other, but somehow due to the documentation it was deployed. Okay, so if you see in this scenario, there was a dependency hell, okay, hardware or a software compatibility. These two problems always occurs. Okay, so the containerization solves this problem. Okay, this complexity is solved by containerization. Okay, and it also has containerization maintains resource separation as well. Okay, so how it is done, we'll see next. So if you see any requirement, any software which is built, okay, we come up with some idea where that will be creating such kind of a software. Okay, then we gather the requirements. Okay, the coding is done, it is tested. After testing, we build and package it. Okay, so this step is very important, building and packaging. Okay, we'll be seeing that soon. So this building and packaging is very important. So the package which is created, that is deployed on the server, this is the traditional application release process generally. Okay. And before going further, we also need to learn about waterfall model, agile, and CI/CD as well, okay, or the continuous deployment. So in waterfall traditional approach, what happens? We design the code, the same cycle, okay, and suppose designing the code took 2 months, okay, then means designing means planning and all. Then the coding took few more months, like 3 months, okay. The testing took again 1 month, and for deployment also it took 15 months. So to overall, okay, in waterfall models, all the steps are done one by one. Okay, before the designing is completed, we cannot start coding. Okay, and before the coding is not done, we cannot start testing. Okay, so one by one, like a waterfalls. Okay, in a waterfall model, everything is done, and suppose it took 8 months. Okay, then in agile water models, what happens is, instead of doing everything at the one go, the the whole project divided into small parts, or also called as sprints. Okay, and there will be a sprint goal. Okay, within that sprint of about 15 days or 1 month, whatever it is. Okay, the sprint goal, every day something will be discussed and every day something will be done. That means in small iterations. So here everything was done at one go. Here also it's done at the one go, but in small iteration, design, coding, and testing. Then after the sprint, again design, coding, and testing and all. So suppose due to this agile methodology, it is a methodology. It is not the like waterfall model. Uh, there are some improvements. Okay, and a bit faster development is done. Okay, now with the same approach of agile. Okay, when we deploy the software. Okay, with a collaborative and automated approach, how it is done is, there is a continuous integration, continuous deployment, okay, and continuous feedback as well. How after designing will take time. Like after designing, the coding is done, okay, then the testing is done, and immediately the feedback is given to the developer. Okay, so this is means everything is fast. It is done in continuous way. Okay, and that's what the DevOps is all about. Okay, continuous integration, continuous uh, deployment, and continuous feedback. So instead of 8 months, it won't take much time. Instead of 8 months, it will take about 2-3 months only to complete the DevOps cycle, to release the software. So you must have seen this image. So here, if you see, everything is continuous. The feedback is given fast to the developer, and if there are any bugs earlier, it gets solved easily. Okay, and now we haven't yet discussed about how the container or the containers look like and what differentiates it. Okay, so in any operating system, okay, we know there is a kernel. Okay, the kernel is the heart of operating system. It interacts with the hardware of the system. Okay, whatever we type, suppose if I'm typing A B C D or mm, anything, then we are typing via shell. Okay, so we understand English language, so via shell will be typing. Okay, and whatever we type will be given to the kernel, and kernel knows the language of the hardware, that is zeros and one. So whatever we write it in English language, it gets converted to the binary format and we interact with the hardware. Okay, so this is how the operating system looks like. Okay, so what when we install in any operating system, okay, on a bare metal means your laptop or a server which doesn't have any VM. Okay, so everything is running on the that particular bare metal itself. Okay, so what we need to do, we need to buy a hardware. Okay, then we install operating system on it, then some language runtime or programming language runtime, you can say, and on the top of that we'll be installing our code. Okay, this is how we do it in a bare metal format. So bare metal, if you see, there will be only a single operating system, and in short a single kernel. Okay, there is only one kernel. Okay, now what happens in virtual machines? Okay, on bare metal, if you see, that most of the resources are not fully utilized. Okay, only for a single container or a single application we are using a large bare metal server. Okay, its resources are wasted. Okay, so what we can do is we can have multiple operating system. Okay, and we can run multiple containers on it. So what we do is we create virtual machines, so we do not need to take care about the hardware. Directly on the VM, like we did it in AWS EC2s, we directly created the VMs. On that we installed operating system, some language runtime, and we can run our code. Okay, that's what happens in virtual machines. And we can have multiple virtual machines. Suppose here, as it is showing, there are three virtual machines. Then on a single hardware there are three virtual machines, three operating systems, and three different kernels. So I'm insisting on kernel. There is a specific reason for it. On a bare metal, single operating system and single kernel. Okay, on virtual machines there will be three operating system, and each operating system will have its own kernel. Okay, but what happens in containers? Okay, in containers we don't even think about VMs. Okay, we directly install a container. Okay, and the container is installed on any one of the VMs. Okay, which has a single OS and a single kernel. Okay, in containers there will be a host machine, generally a VM. Okay, that host machine has a single OS and a single kernel, and on top of that we'll be installing a container and we'll have the code. So there won't be only single container, we can have multiple containers. So suppose as shown in this diagram, there are six containers. Okay, so all the six containers will not have six operating systems. There will be only one OS on the VM. Okay, and on that VM there will be an OS, and that OS will have single kernel. Okay, and multiple containers. So multiple containers means there will be only the code, okay, along with the dependencies. Only code along with the dependencies. We'll see that next. And there is also functions options, okay, in which we do not even worry about the container. Directly we run the code, that is called as serverless. Okay, so we'll be mostly concentrating on containers. So just now whatever we saw, the same thing is given here. There will be in a hardware, operating system, and operating system we have applications. Okay, in virtualized environment, instead of a single operating system, we, due to virtualization, we create one more multiple virtual machines. Okay, there we have operating system, some binaries and libraries, like that is dependencies, and on top of that we create the applications. Okay, in container what we do is single operating system, a container runtime. Okay, so Docker is one of the container runtime. So whatever is required to run the container, that is called as container runtime. And here what we will do is we'll have multiple containers on a single operating system on a single kernel. Okay, so if I have a HTTPD container, that will be separate. Okay. If I have Nginx container, that will be separate. If I have a MySQL container, that will be separate. Okay. All these containers will have its own binaries and libraries and an application code. Okay. If we install it on a single operating system, we cannot have multiple versions of Java or any software. But on a container, on a single system, due to the isolation, the containers are in isolation. Okay, all the containers will have different version of the binaries, okay, and different code, and they won't interfere with each other. Okay, so the resource separation is done and the isolation is also done. Okay, so in our example where the developer and the operations guys were fighting, the solution would be the developer will create a container with whatever dependencies, okay, like the JDK version, correct JDK version, and the whatever software dependency softwares are required. He'll create a single image of it. Okay, we'll also be learning how to create that image. He'll create a single image and he'll give that, use this container. How to use that we'll see later. Okay, that as it is, the container will be picked and it will be deployed somewhere else, and there won't be any dependencies issues or dependencies issue of libraries and binaries. Okay. So how the containers work or how they are created. So the containers, they are mostly Linux containers, and Linux kernel has some features. Okay, chroot, namespaces, and control groups. These are the system level internal features of Linux kernel. Okay, that paved the way for creating the containers. So in containers, okay, there is a concept called chroot. Okay, in chroot we are not allowed to see all the directories. Okay, will be restricted. So if you see it here in the previous slide, they all three containers are they are isolated. They won't interact with each other. They cannot see each other's directories and files. Okay, so this feature helps us in creating a container. Then the namespaces. Okay, we cannot see other PIDs, that is PIDs means process IDs. Okay, due to the namespaces we cannot see the other process IDs. And the third one is control group. Okay, in control group we can do the resource management. Okay, so this control group will say that you have been allocated this much amount of CPU and memory, and you will not get more than that. Okay, so instead of one single container taking all the resources, the proper resource management is also possible due to the kernel feature of control group. So the containers are generally based on two concepts of Linux kernel. One is namespace, okay, control what a process can see, and the other one is, other kernel feature is C groups, control what a process can use. Okay, so if you go again into low level, the namespaces are having PID, mount, network, and all, and C groups are also segregated, but we don't need to go much deep into it. We just need to remember that namespace and C groups, these are the two kernel features due to which the containers run properly and are created. Okay, so again a detailed discussion on C groups. Okay, so C group was created by Google. Okay, in 2006, one of the engineers created that. Okay, and this feature of Linux kernel isolates and control the resource usage for user process. Okay, so as the containers are segregated, it is important that the processes and the resources are properly managed. Okay, so in C groups, what happens? Process can use lot of memory. Okay, and one of the process will say that I want 10 GB of memory. Other process will also say 10 GB. Okay, but the kernel will say that I have this much amount of memory only, and I'll allocate it, okay, as per the definition given. Okay, so it is again, if you read it here, a C group is a group of processes. Okay, every process in container is in the same C group. C groups have memory and CPU limits. you three get 500 MB of RAM to share. Okay, that is, and if there is a too much memory usage, okay, then it won't be given more memory. If the limit is 500 MB, then you will have to use only that much. Okay, we can increase it, but that's the quota defined for it. Okay, and suppose due to some process there is a lot of CPU usage. Okay, then it will say you have your quota limit is exceeded, you will have to wait. Okay, so all these things uh, make containers run properly. So we have seen this image. Okay, so in a traditional virtual machine we have a server. Okay, it will have an hypervisor. Okay, VMware is one of the hypervisor. Then the multiple OS and applications. In containers, the single kernel, single OS. Okay, and multiple containers with set of their own binaries and libraries. Okay, Linux C groups paved the way for technology called Linux containers. So LXC, okay, we also call it as Linux containers. We have seen this. Okay. So till now we learned about container. So let's also learn about its definition. Okay, a container is an isolated and lightweight unit package. Okay, and what that lightweight unit package contains? An application along with dependencies. Okay, so the container, you should not forget, along with the dependencies. Okay, because there is a problem of dependencies in a production and a development environment that the container solves. Okay, and what is containerization? Managing the containers. Okay, so we created the container, but we need to manage it, and that process is called containerization. Now, how is container and Docker related? Okay, so Docker is the name of the company, okay, who is promoting, or you can say they were the first companies who made the containers available, okay, publicly and also at the enterprise level. Okay, so it is one of the platform, okay, company which gives a platform for the containerization. Okay, and even though it is a platform, it also has a Docker engine, which is a core component of Docker, due to which we can automate or manage the proper containers. Means how the containers are managed on a particular host. And the Docker promoted it so well that instead of container, we also call the container as Docker. Okay, but Docker is not the only one company which provide containerization. There are many companies like Rocket, RKT by CoreOS, LMCT5 by Google. Okay, there are other Docker containers, container technology as well, and we'll see this later. There is a process how the containers are built, okay, from the images that is shown here. Okay. So let's go back to how history of, you can say, containers. Okay, so earlier the LXC release was done in 2008. Okay, then 11 OpenShift came, then the Rocket, Docker. Okay, and nowadays if you see at the end, we can see Builder Podman. Okay, so as I said, Docker is not the only container technology. There are some others like Builder and Podman. Okay, so the most of the Red Hat people prefer this. Okay, those who use Red Hat, on Red Hat, the Builder Podman is the default one instead of Docker. So some of the alternatives to Docker, LXC container is still there. Windows Hypervisor also gives us possibility to create containers. Then RKT, Podman, Runc, and Containerd. These are some alternatives for Docker.